Today we're going to be talking about limits at infinity, and we'll be looking at how if x goes to positive or negative infinity, we'll look at the end behavior of graphs, and in that sometimes we'll be able to discover, oh, there's a horizontal asymptote in a particular graph, the graph of a function. So in the first example, I already have the graphs marked up for you. You can just observe them, that we were talking about the limits as x approaches infinity. And as x approaches infinity, positive infinity of the graph of 1 over x, then you can see that the function goes to 0 and it's above the x-axis. And then the limit as x approaches negative infinity, our function goes to 0. So we've got that. If we're looking at e to the negative x, the limit as x approaches positive infinity, we can see that that's our limit is equal to 0. And the limit as x approaches negative infinity, we can see the graph going upward, it's equal to positive infinity. It diverges. So often we use those two words, converge and diverge. Converge to a value, so that would be here on the right, and on the left, the function would diverge to positive infinity. So if we look at the next graph, it's the graph of the tan inverse, often called the arctan. So we can see that as the function, as the limit as x approaches infinity of y, we'll call it tan inverse, we'll just write it out, tan inverse of x, then that looks to be equal to pi over 2. And we know that pi over 2 is the horizontal asymptote. So I'm going to go on to the pen at this point. Y is equal to pi over 2 is the horizontal asymptote on the top of the graph. And then if we look at the bottom of the graph, we have the limit as x approaches, that's not a good color, let me switch over to a better color. The limit as x approaches negative infinity of the graph of tan inverse of x. And we see that that's equal to negative pi over 2. Okay, and we can see that as you come out here, then the function approaches that horizontal line, y is equal to negative pi over 2. Okay, so as we move along here, I have a couple notes for you to take notice of, that the limits at infinity in horizontal asymptotes, just highlight what you are looking at here. Let f be a function defined on some interval, so from a to infinity, and the limit will then, as x approaches infinity of f of x equal L, that means the value of f of x can be made arbitrarily close to L by taking x sufficiently large. So if we look at a couple of examples of what these look like, a more intuitive way of looking at it rather than such a wordy kind of thing. So let me go to purple here. So if I look at a graph such as this, they might have some other behavior. But as x approaches infinity, you can see that the graph is approaching L. If we consider one sweeping down towards an asymptote, once the line swings down to L, it doesn't turn around. It continues to follow L to infinity. Or we could have a graph that looks something like this, where it oscillates back and forth till the cycles get very small, very tiny, and it moves to infinity in such a manner, wrapping around the horizontal asymptote y is equal to L. So if we look at the definition about moving towards negative infinity, if a function is defined on some interval that is open from negative infinity to a, then the limit as x approaches negative infinity is equal to L. It means that the value of f of x can be made arbitrarily close to L by taking x sufficiently large negative. So a couple of examples there as we move in the negative direction then with our function. If we have a function that kind of moves down and sweeps down and looks something like that, our function moves towards L. L is a horizontal asymptote. So we could also look at a function moving to negative infinity. It might go something like this. It might do something other, but you can see as x moves to negative infinity, that your function moves towards y is equal to L. Same thing here as x moves to negative infinity over in that direction. So far, can't be counted. So then we know that the limit as x approaches infinity of f of x is equal to L, then we can say that y equal L is a horizontal asymptote of the function. The initial functions on page 1 all had horizontal asymptotes. So then we've got this next theorem. In your book, I believe it's theorem 4, but it changes with textbooks. That's in Stewart's 5th edition. So if R greater than 0 is a rational number, then we have this limit. The limit as x approaches infinity of 1 over x to the r is equal to 0. So as x gets really big down here in the denominator, as x gets really big, this whole fraction goes to 0. The same thing can be said if x approaches negative infinity. However, we want to be aware that there are things that become undefined, such as square roots. So if I take the limit as x approaches negative infinity of 1 over x to the 1/2, that's really the square root of x. And recall, you're putting negative values in, and that would make this undefined, this being 1 over x to the 1/2. So we've got to be careful with some of our expressions, so that's why we have a little clarification there. So let's look at limits of some of these functions. So find the following limits. The limit as x approaches infinity of 1 over x squared is equal to, we'll just plug away. Here we've got 1 over infinity squared, which is equal to 0. And we would call that a positive 0, but nonetheless a 0. We have 5 over x cubed for the next one. So the limit as x approaches negative infinity of 5 over x cubed. That would then equal 5 over negative infinity cubed, which is equal to 5 over negative infinity, and negative times a negative times a negative is still going to be negative, which would then be negative 0, which is still 0. Okay, and then for the last one, we have the limit as x approaches infinity of 5 over square root of x. So that would be then 5 over the square root of infinity, which is equal to 5 over infinity, which is equal to plus 0, which is equal to 0. Okay, now note on this last one, we can't take the limit as x approaches negative infinity of 5 over the square root of x here, because the limit does not exist, because the function does not exist here. You can't take the square root of a negative number. Okay, so now using this simple little limit, as it turns out, it's going to be very convenient to use the limit as x approaches infinity of 1 over x to the r form, because we take a look at the following limit now, where we're approaching infinity. We get the following result. We get 3 times infinity to the 4th, let me erase this little arrow here, 3 times infinity to the 4th power, which is still going to be infinity, plus 5 times infinity squared plus 1, and then that would be over infinity to the 4th power plus 6. Now this is all addition here, so picture this, you're adding a really huge number to another really huge number plus 1, and you get another really huge number. In the bottom we have infinity to the 4th plus 6, and that's going to be a really huge number, uncountable. As it turns out, infinity divided by infinity is an indeterminate form. So it's an indeterminate form, and you've come across these before, and such as 0 divided by 0. And this came about in chapter 2, and what we did was we manipulated the expression. So that's exactly what we're going to do, but we have a different manipulation for this particular one. So we go back to our original expression, 3x to the 4th without the limit, plus 5x squared plus 1, and that's over x to the 4th plus 6. Now we're going to do some weird factoring here. We're going to pull out Oh, no, we're not going to do weird factoring. I'm sorry. What we're going to do is we're going to take the top of this fraction and we're going to multiply by 1 over the highest power in the denominator, which is x to the 4th. If you notice, x to the 4th plus 6. Now recall, you're going to distribute, when we're multiplying the top, distribute on the bottom. So let's multiply this and see what we get. We get 3 plus 5 over x squared plus 1 over x to the 4th, all over 1 plus 6 over x to the 4th. Okay, now let's take the limit. So here's the first part. We manipulate the expression. We just use a little algebra. The second part is, now we're going to try to take the limit again. The limit as x approaches infinity now of 3 plus 5 over x squared plus 1 over x to the 4th, and that would all be over 1 plus 6 over x to the 4th. As a result, we get 3 plus 0, because the limit of 5 over x squared is 0, plus 0 over 1 plus 0, which turns out to be 3 over 1. Therefore, for our final answer, the limit as x approaches infinity of 3x to the 4th plus 5x squared plus 1 all over x to the 4th plus 1, x to the 4th plus 6 is then equal to 3. Okay? All right. Now let's try another one. I'll let you go back and move backwards and forwards if necessary. Oh, I think I have one more to do, right? Okay, so let's look at the limits of power functions. If we have the limit as x approaches infinity of x to the 3rd, then we really just plug away and we get infinity to the 3rd power, which is infinity, right? Okay, good to go. If we have the limit as x approaches negative infinity of x cubed, then that would be negative infinity cubed, which would be negative infinity. 3 negative factors, still negative, or it becomes negative. Then if we have the limit as x approaches negative infinity of x to the 4th, we get negative infinity to the 4th power. We know 4 negative factors would give us then a positive infinity. And this kind of holds true with the graphs that we know for x cubed and for x to the 4th. So x cubed, as you well know, looks something like that. X cubed looks like this, kind of like a flat parabola around the origin. Okay, and you can kind of see where as x goes to infinity, we get a good color here, as x goes to positive infinity, the first example, number 1, then the function goes to positive infinity. As for number 2, as x goes to negative infinity, the function goes to negative infinity. And for x to the 4th, it doesn't matter which direction, but we have negative infinity here. As x goes to negative infinity, then you can see that the function x to the 4th approaches positive infinity. And the same is said with if x goes to positive infinity, then the function also goes up together with the negative infinity limit. Okay, so now what about a general polynomial? So what we do here is if it's all addition, we can look at it and we could say, well, that's going to be positive infinity plus 1, which is going to be positive infinity. But to prove the limit, we want to factor. As I said before, we have a lot of weird factoring. So I'm going to let if we look at the limit of this as x goes to infinity of f of x, that's going to be clearly infinity plus 1, easy to see, because it's all addition, which would then be infinity. The question is, what happens mathematically when we say the limit as x goes to negative infinity of f of x? Because now you're dealing with the following result, where you have x to the negative infinity, or x would be negative infinity, so we have negative infinity to the fifth would be negative infinity to the fourth would be positive infinity, negative infinity to the third would be minus infinity, and then you have plus 1. So what is the deal with this, or how do we prove it mathematically that those infinities would all head more towards negative infinity or positive infinity, or which would the result be? So here's what we do. As a result, this one, the answer to this one, is going to be positive infinity. But let's show how we would do it with another example. So what we do first is we do some weird factoring. I like to call it that because generally I get students who are not comfortable with this kind of factoring when they first come into a class, and they kind of like, what is this? What? Okay, so we'll take the limit then as x approaches negative infinity, and we're going to factor out the highest power. Factor out x to the fifth. Generally the response is, you can't do that. Sure you can. So let's factor out an x to the fifth. X to the fifth, and I'm going to put up a bracket. So that leaves a negative 7 minus 6 over x squared plus, oh, I'm sorry, that's a plus 6 over x squared plus 1 over x cubed plus 1 over x to the fifth. Okay, so we factored out. Remember, when you factor, you divide each term by x to the fifth when you pull it out front. Okay, so here, let me fix my bracket style here. So now we're ready to take the derivative. Okay, I did not really need that first parenthesis, but let's pair it up. So we're not ready to take the derivative, are we? We are ready to take the limit. So I'm going to plug in negative infinity to the fifth power. And think about this for a second. That's going to be negative infinity to the fifth power here, but the limit of a constant is a constant, and this becomes 0. 6 over x, as I put in negative infinity, that becomes 0. 1 over x cubed becomes 0, plus 1 over x to the fifth becomes 0. So now, let's see what we have now. We have negative infinity times negative 7. I'm going to put this negative infinity because negative infinity to the fifth is negative infinity times negative 7. This all turns out to be then positive infinity. So now we have our limit. So our limit is positive infinity. Let me box it up and put it in a nice color here. So our limit is positive infinity. So a way to prove it mathematically. Though many of you studied the end behavior of graphs in pre-calculus, and this would make a lot of sense, and then you open up your graphing calculator and the same thing is said to be true, but we've proven it mathematically. Okay, one more that we have to do then, and then we'll be finished for this lesson. We have find the limit of this expression. If we put in infinity first, we notice that we have, let me see, it's going to be infinity plus 2 over the square root of 9 times infinity squared plus 1. So it looks like we get infinity in the numerator, and then that's going to be over some kind of infinity again. So we have an indeterminate form, which is going to require that we manipulate our expression. Okay, we've got to get around the indeterminate form. So we're going to go back, step 1 again, and we're going to manipulate the same way we did it with the first example that I did tonight. Example number 4. So we've got x plus 2 now. And now what I'm going to do is some weird factoring again. So we're underneath the square root, and I'm going to factor out an x squared. When I do, that leaves me with 9 plus 1 over x squared. Okay. So then I'm going to take this, and I'm going to say, okay, that's x plus 2 over the square root of x squared times the square root of 9 plus 1 over x squared, which is then equal to x plus 2 over the absolute value of x times the square root of 9 plus 1 over x squared. Okay, recall as I say this that the square root of x squared is equal to the absolute value of x, okay, and not just x. So now that we have this expression, that's our expression with little manipulation. And you can see where I have that 1 over x squared. You're wondering what's going to go on there, right? Here we go. Step 2. We are now ready to take the limit. Now, I want you to think about the absolute value of x. Remember, you have x's that are positive, and you have x's that are negative over here. So, and then you have 0 in the middle. So, we're heading now first, we'll head in the positive direction towards positive infinity. So, we're looking at our expression, but I want to highlight this absolute value of x down here, so that as we head in the positive direction, in the numerator we still have x plus 2, but in the denominator we have the following. The absolute value of x, if x is positive, is simply x, followed by the square root of 9 plus 1 over x squared. So let's address this then. The absolute value of x on the number line would be just x over on the right hand side of 0. And we'll talk about the other side when we get to it. So now, can you see we have an expression x plus 2 in the numerator? So now I'm going to do the same thing I did with the rational function. I'm going to take the numerator and I'm going to multiply by 1 over the highest degree in the denominator, the highest power in the denominator, which is just x, and do the same thing in the denominator. So I'm multiplying by 1 essentially. I'm going to put parentheses around the numerator and around the denominator. And now let's simplify. So now I'm going to extend the page just a little bit here. I'm going to place this over here. So this limit then is then equal to, it's the limit as x approaches infinity of x times 1 over x, let me scroll that down just a little bit, would be 1 plus 2 over x all over the square root of 9 plus 1 over x squared. So that limit then could be taken directly, and it is 1 plus 0 over the square root of 9 plus 0. We end up getting 1 over the square root of 9, which is, of course, 1/3. Therefore, the limit as x approaches infinity of our original function, x plus 2 over the square root of 9x squared plus 1 is equal to 1/3. Okay. In this problem, though, we're only looking for the positive absolute, the positive, I'm sorry, let me go back. We're looking for the limit as x approaches positive infinity. So let's add just one more page here. And I'm going to do the limit of the same one. The limit, except I'm going to move towards negative infinity. You have some homework problems like this, of x plus 2 over the square root of 9x squared plus 1. But we'll use part of the results because we already know that this is equal to the limit as x approaches negative infinity of, we'll write it with the absolute value of x plus 2 over the absolute value of x times the square root of 9 plus 1 over x squared. We don't have to repeat all that algebra that we did. If you recall, though, where we have 0, the absolute value of x is x if x is on the positive side of 0. But if it's on the negative side of 0, it's equal to the opposite of whatever x is, because now x's are negative. Consider if you take the square root of negative 3 squared, which is equal to the absolute value of negative 3, which is equal to a positive 3, which is equal to the opposite of negative 3. So, evaluating this, then we would have the limit as x approaches negative infinity of x plus 2 in the numerator, but now we would have the opposite of x times the square root of 9 plus 1 over x squared in the denominator. So let me tidy that up a little bit. Looks like my plus sign is running into my fraction there. Okay, so now we're going to do the same thing we did before, and we're going to multiply by 1 over the highest power in the denominator and simplify. So, grouping in the numerator, grouping in the denominator. So, here we go. In the numerator, I have the same thing. So we have the limit as x approaches negative infinity of 1 plus 2 over x all over the negative. We're going to take this negative x and multiply it by 1 over x. Recall, you don't have to distribute when you have 3 factors. We're just multiplying these two together. So we get 1, or negative, the square root of 9 plus 1 over x squared. We're ready to take the limit now, so that turns out to be 1 plus 0 over the negative of the square root of 9 plus 0, which is equal to 1 over the negative square root of 9, which is equal to negative 1/3. Even though I didn't have that problem there, we want to say that the limit as x approaches negative infinity of x plus 2 over the square root of 9x squared plus 1 is equal to negative 1/3. Take out your graphing calculators, and you want to take a moment to examine your graph at times. Remember, you need a parenthesis around the numerator, and then you're going to need, you have the square root as a grouping symbol. Some of you will need to put a parenthesis if you have an older model calculator, because the parenthesis comes up first in front of the 9. But graph that and examine, when you graph it in your calculator, you'll examine, where are the horizontal asymptotes? Do they make sense? You have now proven them mathematically. So the two horizontal asymptotes, 1/3 and negative 1/3. There is some team practice here if you want to give it a shot, and I'll post the answers for those. Have a great weekend. I'll see you next week. Some of you, not, happy Thanksgiving.